All right, let's get started. My name is Vibha Viswanathan. I work for Microsoft. In the last 10 years, I've been working on CPU, GPU, caches, memory subsystem, and things like that. Um Today, memory ordering and cache coherency is my favorite topic, and it's my honor and pleasure to actually moderate this session for all of you. Um, just a little bit on the topic. When I talk of memory ordering and cache coherency, it's a it's like a slippery fish. You think you caught it, and then next moment it actually slips away. The problem is you do when you do a unit level, and then you go to a single core level or a subsystem level, or on the whole SoC, which has maybe tens and 50s or that many CPUs, and you have a GPU and PCI subsystem and all of that, some of the IO devices. The complexity of memory ordering with the DDR and everything in picture, it becomes very complex. And I always when I read new papers and um, listening through very experienced architects and designers and new way of verifying things, your perspective changes. And today is my pleasure to moderate this session for you. And having said that, we actually have 3 papers today, um, talking on, actually interestingly, on various aspects. How will you create a really reusable, scalable checker, right? That does memory ordering and coherency and things like that. And then how will you generate interesting stimulus? That's another aspect. And then when you create a multi-core environment, how do you create a cache model which actually has a lot of APIs that can be that can actually help you to predict the newer values and things like that. So I'm not going to talk too much into those details. The authors are going to actually talk about it. But before we jump onto the session, a couple housekeeping rules. So this is going to be a recorded presentation, and then if you have any questions, hold on to the questions, and at the end of the presentation, we will have a few minutes to actually ask questions. And the first paper is by Subramoni Parameswaran. He is a principal verification engineer at Xilinx with over 15 years experience in the field of design verification. He has led verification cutting edge designs like adaptable intelligence engine and Zinc ultrascale plus multiprocessor system on the chip products. He was honored to be awarded the Ross Freeman Innovation Award for his contribution to the architecture and verification of the network on-chip design at Xilinx. In prior roles, he was part of a successful startup, Soft Machines. He led international verification team responsible for from scratch design of microprocessor. Subramoni holds a master's degree in electrical engineering from University of Colorado and an MBA from Santa Clara University. With that, please welcome Subramoni to present the paper for us.
Hello, my name is Subramoni Parameswaran, and I'm a principal verification engineer leading network on chip and artificial intelligence verification at Xilinx. In this presentation, we will talk about the modeling of memory coherency in the presence of concurrent or parallel accesses. The agenda for the presentation is the following. We will start by describing the problem of modeling memory coherency and the current approaches used and their pitfalls. We will introduce the concept of window of uncertainty, or WOU for short, which will allow us to lay the foundation for a different approach to the problem. Then we will describe how the concept of window of uncertainty allows us to model uncertain outcomes in the presence of multiple outstanding writes. We will follow that by tackling the problem of simultaneous outstanding reads and end with a conclusion. As you may know, memory coherency is a principle that guarantees the value at a single memory location for a read. When there are multiple writes to a memory location, memory coherency requires a read to return the most recently written value. As you may be aware, it may not be easy to precisely predict the most recently written value when different actors are present or when different transaction types, like writes and reads, have completely different latencies. It also becomes difficult to predict the value when there are multiple outstanding writes or if reads are outstanding at the same time as writes. In the next slide, we will talk about the current approaches to the problem and their pitfalls. Current solutions include cycle-accurate modeling of the design or observation of internal design variables. Obviously, these solutions have their pitfalls. Cycle-accurate modeling of the design is very expensive and error-prone, leading to lots of debug. There are usually many failures, which leads to a lot of time spent on verification closure. Observation of internal design variables hinders true verification. It could lead to potentially incomplete verification and missed bugs. Furthermore, it reduces test bench adaptability to changes in design. Instead, in this presentation, we will propose a different approach to address this problem by modeling the inherent uncertainty of read outcomes in the presence of concurrent and parallel writes and reads. During the course of this presentation, I hope to convince you that rather than trying to precisely determine the exact value that should be coherently returned by the design, the better approach would be to store multiple values that can be a potential match for a read. All the multiple values that are stored would, of course, be coherent possible values. The advantages of this proposal are that it does not require cycle-accurate prediction of the design or observation of internal design variables. In this section, we will introduce some definitions and the concept of the window of uncertainty, and this will build the foundation for our proposed solution to the problem. Let us start by defining some important terms used throughout this presentation in the context of a transaction. As you know, the term issue of a transaction is used to refer to the start of the write or read transaction at the design boundary. The term acknowledgement is defined as the earliest of when a write or read response is provided by the design or the unique write transaction value is visible to a subsequent read. Another way to think about the term acknowledgement is that the design is required or guaranteed to have seen the write. The term outstanding for a transaction refers to the time window from its issue until its acknowledgement. This slide explains why some read outcomes can be uncertain. In this case, there are two writes outstanding simultaneously and a read that is outstanding in parallel with the two writes. The read system could coherently return either the value of write 1 or the value of write 2 because both are active at the time the read is issued. Coherency rules cannot help us determine whether write 1 value or the write 2 value should be returned by the read. Therefore, by definition, the value that is returned by the read is uncertain, and it could be either of those two values. We could, of course, try to deterministically predict precisely which value it would return, but as mentioned before, deterministic result prediction is expensive and or error prone. How can we model the uncertainty introduced by a write? The first thing to note is that the uncertainty is finite in time. In other words, it is a time window where the value of a write persists. The start of uncertainty is always the time of issue of the write. The end of uncertainty is when the write value must be superseded by other writes in accordance with coherency rules. In other words, it is no longer possible that a read can return the value that was written by this particular write because other writes must have overwritten that value, and hence the read is required to return the overwritten value. Now that we understand the window of uncertainty, we will use this concept to deal with multiple outstanding writes. In this section, we will consider multiple outstanding write cases for the same actor versus different actors. In the next few slides, we will consider how the end of the window of uncertainty is different when writes are issued from the same actor versus when the writes are issued from different actors. Understanding the end of uncertainty and the WOU in these different cases will suggest a data structure or a storage structure that can be used to trim or delete incoherent expected read values such that we can keep all the potential coherent values that are allowed to be a match per memory location. In this slide, we more precisely define the end of the window of uncertainty for writes from the same actor to the same memory location. Consider, in this case, write 1 and write 2 from the same actor. Write 2, in this case, is issued after write 1. Write 1 completes, and then subsequently write 2 completes. Because write 1 and write 2 are from the same actor, and because write 2 is issued after write 1 must be superseded or overwritten when write 2 is acknowledged. In other words, if write 1 and write 2 are from the same actor, to the same memory location, and write 2 is acknowledged, the write 1 value can no longer persist, and hence the window of uncertainty for write 1 has to end when write 2 is acknowledged. As mentioned before, the start of the window of uncertainty is always the issue of write 1, but the end of uncertainty for write 1 happens when write 2 is acknowledged. Consider a read now that is issued after the end of the write 2 acknowledge. It must always see the write 2 value, and it can no longer coherently return the write 1 value. This statement is true even if write 1 and write 2 were simultaneously outstanding, as is the case shown in the picture. Both are active at the same time. And it's worth mentioning that this statement is true only because write 1 and write 2 are from the same actor. Now, let us switch to looking at the window of uncertainty for different actors when there are multiple outstanding. How does the end of the window of uncertainty change for two writes issued by two different actors to the same memory location? This slide talks to the difficulty in determining the end of the window of uncertainty for two different actors when there are two or more outstanding transactions. In this case, the latencies experienced by each write 1 and write 2, could be very different. We show in the top picture that write 1 and write 2 have similar latencies. And in the second picture, we show write 1 has a very long latency and write 2 has a very short latency. Because of the different latencies experienced by write 1 and write 2, even though write 1 was issued before write 2, it could be the case that write 2 actually overtakes write 1 and writes into the memory, and then subsequently write 1 writes into the memory. In the bottom picture, write 2 is seen by the design ahead of write 1, even though write 2 was actually issued after write 1. In the top picture, on the other hand, write 1 is seen by the design first, followed by write 2. In other words, write 2 value supersedes write 1 in the top picture, and in the bottom picture, the write 1 value supersedes write 2. From the black box perspective, on the outside of the design, we can only see the issue and the acknowledgement of write 1 and write 2. But the internal design implementation determines the order in which write 1 and write 2 are observed. Therefore, the order of issue or the order of acknowledgement of write 1 and write 2 cannot be used to determine the order in which those values will be observed by the design. Said differently, coherency rules allows uncertainty in the case where two writes are from different actors and they are simultaneously outstanding, and we need to model this uncertainty by capturing multiple values. This is why the window of uncertainty introduced by write 1 is shown as not terminating, even though write 2 is acknowledged. We cannot distinguish the top picture from the bottom picture by just observing the boundaries of the design. So we allow the window of uncertainty to be longer in this particular case when the two writes are from different actors and they are simultaneously outstanding. Having covered this case, in the next slide, we will show that there is one special case which allows us to precisely predict the end of uncertainty for writes from different actors under certain circumstances or a special case. This slide shows the special case for two different actors when the end of uncertainty can actually be determined. This is a serialized write issue case. In this case, write 1 is issued and write 1 is acknowledged, and subsequent to write 1 getting acknowledged, write 2 is issued. Because write 2 is issued after write 1 is acknowledged, coherency rules guarantee that write 2 must supersede write 1 when it is acknowledged, despite write 1 and write 2 being from entirely different actors. The critical detail here is that because write 1 and write 2 are from different actors and can have different latencies, write 2 must be issued after write 1 completes for write 1's window of uncertainty to terminate when write 2 is acknowledged. The number of cycles allowed between write 1 acknowledge and write 2 issue is not required to be a specific value. There could be one or many cycles delay between the end of acknowledgement of write 1 and the issue of write 2, and the window of uncertainty for write 1 would still be terminated when write 2 is acknowledged. If a read were to be issued after write 2 is acknowledged, it is guaranteed that the read would see the write 2 value in memory. Given that we have explored some of the principles and uncertainties related to memory coherency a little further, we can now devise a way to hold the multiple potential values that can be coherent per memory location. We are going to store multiple potential values at the granularity of the memory, which is determined by the smallest write size. We store the multiple data values that might be the winner for that memory location. We order the potential values in this potential values queue, based on the time of issue of the writes. And then once we set up the potential values queue, we can proceed to remove superseded writes based on the two WOU rules outlined in previous slides. This might seem a little abstract at this point, so we will show the creation of the potential values queue in more detail with a couple of examples in the next slide. Now we will explore two specific examples which show how the potential values queue gets populated. On the left, we have the case where a single actor issues both write 10 and write 13 in that order. Both are simultaneously outstanding, and both get stored in the potential values queue in the order in which they are issued. However, when write 13 is acknowledged, write 10 is superseded and removed from the potential values queue. On the right, we have the multiple actor case where write 1 is issued by actor 1, then it completes, then write 2 gets issued by actor 2, and then when write 2 completes, write 1 would be removed from the potential values queue. Until write 2 completes, write 1 has to continue to remain in the potential values queue because it could be coherently returned by a read. These two cases were covered in the previous slide, and with this example, hopefully it should be clear that we can store multiple values per memory location, removing the values that are superseded, thereby deriving all the coherent values that can be returned by a future read. In this section, we will cover the case of simultaneous outstanding reads, because we have not talked about reads that are outstanding at the same time as the writes that were previously issued. We need to develop some special mechanics to deal with simultaneously outstanding reads, and this section will cover that. Thus far, we have developed a framework for dealing with multiple writes outstanding. If it were guaranteed that there would be no writes outstanding when reads are outstanding, we could simply get the potential expected values for each read from the potential values queue. In reality, however, both reads and writes are simultaneously outstanding. The main problem with using the potential values queue on its own is that some writes might be superseded while the read is outstanding, but despite the writes being superseded, the read could return the superseded write value when it completes. In other words, the window between the read issue and the read completion is a window where the potential values queue could change and certain entries could be removed, but those removed entries could still be returned by the read when it completes. If we think about this carefully, we will realize that each read can return potential values from the potential values queue at its time of completion, or any writes superseded in the time interval between its issue and its completion. Said another way, each read can return values in the potential values queue at its time of issue and any outstanding write values between its issue and its completion. If we look in the potential values queue at the time of completion of each read, we will capture all potential write values it could match against, but we would miss superseded write entries that were removed while the read was outstanding. To capture superseded write entries while the read was outstanding, we need to create a per read active reads queue. This active reads queue on a per read basis would store the writes that were superseded while the read was outstanding, and we will show this in the next slide with a more detailed example. This example shows how the active reads queue can solve the problem of reads and writes that are simultaneously outstanding. On the left side, we show how the events unfold in time as time progresses from top to bottom. On the right, we show the final state of the potential values queue and the active reads queue after all these events have occurred in time. In this particular example, we issue 3 writes from the same actor, write 1, write 2, and write 3. Note that the completion of write 2 would cause write 1 to be superseded. Similarly, the completion of write 3 would cause write 2 to be superseded. This is because write 1, write 2, and write 3 are all from the same actor. After issuing 3 writes from the same actor, we now proceed to issue a read, read 1. Meanwhile, write 1 and write 2 both complete, and because write 2 completes, write 1 gets superseded. When write 1 gets superseded from the potential values queue, read 1 is present in the active reads queue, and as a result, we add the superseded value of write 1 into read 1's active reads entry. When read 2 gets issued, and after that, write 3 completes, causing write 2 to get superseded, we remove write 2 from the potential values queue and add write 2 into the active reads queue for both read 1 and read 2, because both read 1 and read 2 are outstanding at the time that write 2 is superseded from the potential values queue. Should read 1 complete at this point, it would expect either write 1 or write 2 or write 3 as the coherent value returned. Should read 2 complete at this point, it would expect either write 2 or write 3 as the coherent value returned. In other words, the potential match for a read is the union of the values that are present in the potential values queue and in the active reads queue at the time of completion of the read. Looking at the order of events in time on the left side, we can easily convince ourselves that this should indeed be the case. Read 1 can coherently return either write 1, write 2, or write 3. Read 2 can coherently return either write 2 or write 3. So setting up the potential values queue and the active reads queue being set up on a per read basis, allows us to use the union or combination of values in the potential values queue and the per read active reads queue to provide all potential matches for each read. In particular, it provides all coherent potential matches for each read. In conclusion, we have developed a coherent generic memory model for uncertain read outcomes. We have dealt with concurrent reads and writes, as well as multiple actors with different latencies. There are many benefits to this model. It seamlessly scales for any and all stimulus, including completely simultaneous reads and writes, no simultaneous reads and writes, and single outstanding transaction across both reads and writes. It leads to improved verification of the design because we can test the design with more concurrent stimulus, and we have a way to predict uncertain outcomes. It reduces the cost of modeling and increases testbench flexibility to changes in design because it removes the need for cycle-accurate modeling and white box observation of internal design variables. Thank you for listening to this presentation. Are there any questions?
Thank you, Subramoni. Thank you for recording that crisp presentation. All the questions Subramoni has been alive, on the sessions, and I think he has been reading through. I think let's take up to another 4 or 5 minutes to answer those questions. Subramoni, let me try to read those questions for you, and then I'm sure you already read them, but just for benefit of everybody, what happens if the writes do not get acknowledgement, that is posted writes? Will the scheme work?
So the definition of acknowledgement was provided in a slide. It probably went too fast. The definition of acknowledgement could be when the write is observed by a subsequent read. So if it's a posted write and a subsequent read observes the value of the write, then from the purpose of this model, for the purpose of this model, we consider the right to get acknowledged, quote unquote, acknowledged. So
Okay.
yeah, short answer is yes, it would work because you essentially use the read acknowledgement, you essentially use the read observation as the acknowledgement for the write.
Okay, thank you. The next question is, does this method help with writes with mismatched memory attributes? That is write back and mixed with write through.
Yeah, this is a really good question. This model is really about coherency rules, and that is kind of the benefit of the model. So whether you implement a write back cache or a write through cache, coherency rules don't change. Right? You expect a write to memory to kind of succeed, no matter how we choose the implementation of the cache. So my belief is, because you are relying on coherency rules and the implementation details don't really matter for the expected value to be observed in the memory, it should work whether it's a write back or a write through.
Okay, thank you. The next question is, does this scheme need to change if the ordering rules change? For example, posted writes can overtake reads from the same source over PCIe, but other link ordering rules might not allow that. So window of uncertainty terminations rule might change with the ordering rule change. Is that correct?
Yes, so I think there is a possibility that you might be able to tweak the window of uncertainty if you have some other ordering rules on top of the standard coherency rules. But in general, if you don't have any additional rules, you can just rely on coherency and predict the expected outcome. But if you know for certain that, let's say, for example, something has higher priority, and the priority based on the time of issue, then of course, you could tweak the model to take that priority into account on a microarchitectural basis. But this model, at least until now, right, without the tweaking that I described, is staying at the architectural level and trying to predict the potential set of expected values for a read. I hope that answers the question.
Yeah, I think it did for me, and I hope for the person who raised the question too, I guess. Go ahead and actually type if you have any follow-up questions. And I'm going to read the next question. Do you really predict the read value or more allow from any of the ones that are allowed? Would you pick up if after the writes ACK, you don't get a consistent read value, but get different values that are allowed? Honestly, I don't understand the question. Subramoni, I don't know if you...
I could use some help. I don't know if Eugene can talk, but I could use some help understanding the question.
Right, okay. Eugene, go ahead and actually unmute yourself and provide clarifications if there is any. Hello, Eugene. Either you're not talking or you're still muted.
So while we are waiting, maybe we can pick up the other question about writes and reads to same location from different actors. There's, I think Neha Jain asked that question. So yes, it would work for writes and reads to the same location from different actors. As was mentioned in the presentation, and there's a lot more detail in the paper, the window of uncertainty is different. So if you have two writes from the same actor, they are the window of uncertainty terminates when the subsequent write is getting acknowledged. But if you have two writes from different actors, you have to make sure that the subsequent write that gets acknowledged is issued after the current write is acknowledged. So in other words, for the window of uncertainty to end for two writes from different actors, there are more rules that are required, right? So if you have two writes from the same actor that are simultaneously outstanding, depending on the order of the writes, you are guaranteed that when the second write completes, it overwrites the previous write. But if you have two writes from different actors, because they could have different latencies, unless they are serially issued, where one write issues, then it completes, then the second write issues, then it completes, you cannot predict the end of uncertainty of write one for two different actors in that case. And I tried to explain that in the slides as well as in the paper. So I encourage you to look at that.
Thank you. I think one last question quickly, if we can. Have you tried formal property checking for this verification? This is from Joe Hopsey.
Right. So this is really about a model that you can use either in formal or simulation. Right. It's trying to explain, it's trying to come up with a way to model the expected values, and then you basically could write a formal property on top of the expected values model. So that way you can prove that for all cases it would hold in formal, but in simulation you might only be able to prove it for the stimulus cases that you exercise. So I hope that answers the question.
Well, we are almost out of time, and but Subramoni, thank you very much for the wonderful presentation and also answering those interesting questions.
Thank you for the questions, and thank you for the moderation.
Great. Let's with that, let's move on to the next presentation. The next presentation is from Nvidia, BatchSolve, a divide and conquer approach to solving the memory ordering problem. The presenter today is going to be Debarshi Chatterjee from Nvidia. Debarshi received master's degree in electrical engineering from Stanford. He's currently with Nvidia as a principal verification engineer. His interest lies in memory subsystem and deadlock verification. Prior to Nvidia, Debarshi has worked at Intel, Broadcom, and Huawei. He holds 4 patents and 6 publications in peer-reviewed conferences and journals. Thank you for presenting today, Debarshi. With that, let's start the recorded presentation. Thank you.
Welcome to DVCon 2022. I'm Debarshi Chatterjee, and today I'm going to present BatchSolve, a divide and conquer approach to solving the memory ordering problem. This work is co-authored by Ismet, Bayraktaroglu, Nikhil, Sathe, Kavya, Shagrithaya, Siddhanth, Dhodhi, and Spandan, Kachhadiya. Memory ordering problem arises frequently in memory subsystem test benches. Let us first understand what this memory ordering problem is. The memory ordering problem aims to find out if there exists a global order given the issue order of memory operations and a bunch of ordering rules. Let's take the example on the right to understand this problem better. Let's suppose that we have 2 sources, source 1 and source 2. These sources could be threads in a multi-threaded program, or they could be BFMs driving memory operations on interfaces. So let's suppose source 1 drives 2 stores, store 1 and store 2, with data X and Y to the address A, and source 2 issues 2 loads, load 1 and load 2, and receives data X and Y again to the same address. Now, since load 1 gets store 1's data and load 2 gets store 2's data, to an external observer will infer that load 1 must be ordered after store 1 and load 2 must be ordered after store 2. And so based on that, there are 2 possible global order that an external observer can infer. Now let us suppose there is a ordering rule which says memops from the same source must appear in global order in the same order as they appear in the issue order. So if this rule has to be obeyed, then you can see that the second global order does not obey that, because in the second global order, store 2 is ordered before store 1, whereas in the issue order, store 2 is ordered after store 1. However, there exists one global order which satisfies the observation of the load data and also obeys the ordering rules. So we will call this execution a legal execution. However, if keeping the problem same, if the loads got the data in the reverse order, then you could see that there are 2 possible global order, but none of them really satisfy the ordering rules. So this kind of execution we will call an illegal execution. As verification engineers, our job would be to run tests, find out if there exists a global order subject to all the ordering rules, and if there's not, then we'll file a bug. And where are these ordering rules coming from? The ordering rules are mainly guided by memory consistency requirements. They could also be arising from deadlock avoidance rules, and usually they are spec'd out in the architectural specifications. There could be link-based ordering rules and so on. The memory ordering problem is very similar to the memory consistency problem, which has been studied thoroughly and is known to be NP-complete. However, there are some differences between memory ordering problem and the memory consistency problem. The memory ordering problem arises in memory subsystem test benches at unit level and integration level, where the BFMs are driving memory operations on the interfaces and doesn't have a direct notion of program order. Moreover, the memory operations that we are trying to order here could be partially overlapping reads and writes, or writes with byte enables hosts, things that are not common in memory consistency problem. And finally here, the ordering rules are guided not just by memory consistency requirements, but they could be ordering rules coming from deadlock avoidance. Although there are differences and similarities, for prior work section, we're going to discuss approaches which have been used for memory ordering problem in the industry at Nvidia and elsewhere. So there are two main very popular techniques. One is the point of serialization snooping technique, which is known by other names in different places. But basic idea here is you're driving memory operations on the DUT, and you track each and every memory operation inside the design using monitors all the way to point of serialization. And then we basically get hints from the RTL to figure out how the design ordered these memory operations instead of inferring the memory operation order. So this works very well because there is no assumption in terms of there's no stimulus restriction, and this can be done in linear time complexity. And the disadvantage is that this method is extremely difficult to port over to different test benches, and also since we are tapping internal RTL signals, any changes to the RTL can cause changes in the tracking logic or serialization code, and so which makes this a very high development and maintenance cost. The other approach is a TSO tool approach, in which this approach uses an assumption that every store has unique data, and so this can be created by just incrementing the store data. So because every store has a unique data, every load will get the store data from a unique store, and so we could draw edges from store to load. And the basic idea of TSO tool is we consider every memop as a vertex in a graph, and we draw edges based on the issue ordering rules, and also edges based on what the load values were observed. And then there is a notion of inferred edges, which I cannot go over in details in this presentation. But the idea is once you draw these edges, we will do a cycle analysis on the graph. And if a cycle is present in the graph, as in this case, then that execution is illegal. Again, this has reasonably good coverage because the assumptions are very limited, and this can be done in polynomial time complexity. However, because of the unique store data requirement, it's very difficult to handle random atomics, and also this method is not very amenable to arbitrary ordering rules. That is, if you have complex ordering rules like PCI ordering rules or other link-based ordering rules, then taking that and generating rules which will generate the inferred edges is a non-trivial problem. The motivation for this work is the need to develop an ordering checking scheme which is portable, low cost, and flexible. So we want this checker to be extremely versatile, as in it should be amenable to various ordering rules like PCI, NVLink, or other ordering rules, and it should be easy to change these ordering rules. And we also want this checker to have very low development and maintenance cost. So at a very high level, the idea of BatchSolve is to specify ordering rules as high-level system Verilog constraints, and then formulate this problem so that the system Verilog solver can handle it. But since it's an NP-complete problem, as the number of memops increases, the ordering to find out global order using the solver scales exponentially. So how do we address this scalability issues? And we do it through something called stimulus batching. In subsequent slides, we'll first discuss how stimulus batching is done, and then we will discuss how we can formulate this problem so that the system Verilog solver can solve it. This slide shows how BatchSolve can be integrated in the standard UVM architecture. The diagram on the left shows a standard UVM architecture. The diagram on the right shows how BatchSolve is instantiated in the scoreboard, and it has a stimulus API. Every sequence in every agent will have a stimulus API to talk to the BatchSolve. So when the sequence generates a memory operation, before sending it to the driver, it will ask BatchSolve for permission regarding sending it to the driver. If BatchSolve says yes, it can send it to the driver. If BatchSolve says no, it will need to re-randomize the memory operations, ask for permission again before sending it to the driver. And this is the mechanism by which stimulus batching happens in BatchSolve, which will be discussed later. But the idea here is BatchSolve basically gets queries from multiple sequences, and it either grants or denies, and by doing so, it acts as a stimulus filter. Okay, so this slide demonstrates a sample output of the stimulus batching code that's there in the bats. So using two addresses X and Y, here with each arrow represents the drive time of a memory operation on the DAT boundary from a source. So as you can see, when various sources start requesting a particular address X and drive them on the interface, for the first few requests, the agents will ask bats for permission to drive this, and bats will, for the first few requests, the bats will grant permission, but it will keep a total count of number of requests sent by all the agents to the DUT. And once that count reaches a certain threshold, then bats internally transitions this cache line state to an almost full state. And what it means, when the cache line transitions to an almost full state within bats will start denying any request to that cache line for a simulation time delta. After the simulation time delta, if any agent asks for the same cache line, it will give conditional grant, and what that means is that the agent should be able to drive a full cache line read to it. And once it does that, the bats will transition this cache line to a full state. Again, what that means is in that full state, bats will not grant any access to that cache line X for a sim time delta. Once that sim time passes, it is good to other agents are again free to reuse that cache line X. One thing to note here is that once a cache line goes into the full or almost full state and bats start denying requests to that cache line, the agents are free to re-randomize the item and generate another address and drive onto the DUT. So by this mechanism, basically bats spaces out requests to the same address from various sources by a certain simulation time, and creating effective batches of addresses, batches of requests to the same address. And because they are spaced out in sim time, if the sim time spacing is sufficiently large, then there is no racing across the requests in different batches. And so we can use the solver now to find the geo across each of these batch and concatenate the geos from the solver to find the final geo across batches. Another way to visualize this stimulus batching mechanism is using this tabular structure. So BatchSolve would maintain a table per cache line, and as various sources sends requests to the cache line, it will put each request or memo in a separate row. So for instance, the first row is saying that at time t1, source 1 made a request which is of type write, and the write basically wrote the first 3 sectors of the cache line. So initially the cache line is an empty state, and BatchSolve keeps granting permission to write to the cache line, but it keeps incrementing the count. And once the count reaches batch size -1, it will go into an almost full state. And from that point onwards, between T9 and T10, it will deny any request to access this cache line. And if after that simulation time threshold passes a threshold delta, it will access a conditional grant, meaning anybody trying to access the cache line can only issue a full cache line read. And we call this a space read. So basically the last request to a cache line in a batch will be a space read. And the reason being so is the reason we need a space read is because we will use the read data returned by the space read as the initial value of the memory for the next batch. So for the 0th batch, we know the init value, but for the batch 1, we don't know the init value. And by issuing a space read, we make sure that the space read does not race with any of the prior transactions or with the second batch transaction in the other batch. So its value can be used as the init value for the subsequent batch. Now that we understand how the stimulus batching happens, let us now focus on how we present the batch to the solver and ask the solver whether there exists a global order subject to ordering rules. So to do that, since the ordering needs to happen at sector level granularity, we take the previous table and filter out everything other than transactions that are going to sector 0. So for instance, the previous table, we had a row at time T4, a source 2 request, which was touching sector 1, 2, and 3, but not sector 0, and that row gets removed here. So other than that, this table is exactly the same with some additional information. So if there is a write, this table has additional information about what the write data is and what the byte enables are. So each sector is, in the sample example, 16 bytes. So it will have 16 byte enables and 16 write data. But for simplicity, we're showing just 2 bytes here. So this is the structure that will be fed to the system Verilog solver, and it will have built-in ordering rules, and the solver will try to see if we can reorder the rows of this structure to generate a global order. And if it succeeds, it will spit out that global order. And if it doesn't, then that means there does not exist a global order subject to the ordering rules. This slide shows the sample system Verilog solver output. For the example shown in the previous slide, the solver was able to find a global order. And so the randomization passed, and this was the output of the randomizer. So in here, you can see the rows which were previously marked 1, 2, 3 up to 9 has been reordered to create the global order. So in this global order, every read gets the previous write data, which has a byte enable 1. So for instance, read 1, the previous write is write 2, all the byte enable 1, so x3 and x4 for the read was obtained from this write. You can see that this read 4 got one of the data from the prior write, but the other byte it got from a write that happened much earlier, and that's because there was no write with byte 1 enable between this write and this read. Let me now try to explain at a high level how the solver would determine whether there exists a global order subject to all the ordering rules or not. To do that, the solver will take an input matrix I, where each row of this matrix is a memo, and the rows are in issue order. And then it generates a unique permutation of n integers called G order using the code here. And then it will use that unique permutation of n integers G order to permute the rows of the input matrix I into a row permuted random matrix P. We will assume that the memops in P, the rows are in global order. And later on, we'll write constraints to make sure that the rows of P are in global order. But for now, we assume that they are in global order and write ordering rules as high-level system Verilog constraints. And this shows a sample ordering rule where I and J are the row numbers in the issue order. And what this is saying, and by the way, G order I and G order J are the corresponding locations of the rows I and J in the matrix P. So what this constraint is saying is that if I is greater than J in the issue order, and they have the same source, Then in the global order also, and they are G order I is greater than G order J. This is another way of saying that memops from the same source must appear in global order in the same order as they appear in the issue order. So although this is a sample ordering rule, there are other complex ordering rules, which like PCI ordering rules, which says posted transaction can pass non-posted, but non-posted will push out posted, or ordering rules involving strict and relaxed order can all be written in terms of high-level system Verilog constraints. So far, we have seen how we can write ordering rules as high-level system Verilog constraints, assuming the rows of P are in global order. But how do we write constraints to make sure that the rows of P are indeed in global order? And this would have been a very trivial problem to solve if all the rows in P were memops with single byte reads or writes, because in that case, the property for global order would be if row I of P is read, then it would just get the data from row I minus 1 of P. And it doesn't matter if row I minus 1 of P is read or write, this property would hold. And this is a property which is very easy to code in system Verilog. But the problem is that these memops are actually reads with multiple bytes, and there are writes that could have writes with byte-enabled holes. And because of that, this property that I just mentioned doesn't hold true. Because you can think that if row I is a read preceded by a row I minus 1, which is a write with byte-enabled holes, then row I, which is a read, will not get the write data for all the bytes from row I minus 1, because row I minus 1 has writes with byte-enabled holes. So how do we write constraints to make sure the rows of P are in global order in the presence of writes with byte-enabled holes? And there are several methods we found to do this, but some of them are more involved than the others, and not each of these methods are extendable to memops other than reads and writes. So in this slide, we're going to share one method which is the simplest of the ones that we found, and it is also extendable to memory operations other than reads and writes. The basic idea here is to create a random dummy matrix M, where the rows of M mimics the data of the memory after the execution of the corresponding row of P. And then once we create this matrix, then we will basically write three set of constraints. One, two between the rows of P and M, and one between the consecutive rows of M. So the first set of constraint, which is shown here, is all it's saying is that if row I of P is a read, then the read data is same as the memory matrix data for that row. The second constraint, all it's saying is that if the row I of P is a write, and let's say a particular byte J has byte enable 1, then equate the corresponding data byte J to the corresponding byte in M, and do that for all J's. And this is what's shown here. So the final constraint says that if a row I of P is a read, then the data bit at this row I and I minus 1 will not change. And if similarly, if row I PI is a write and certain bytes J have byte enable holes, then for those bytes the data won't change across the consecutive rows. And so with these three constraints, if we solve together, we'll make sure that the rows of P are in global order. And this separately, we have written ordering rule constraints. So if we solve everything together, we will see if there exists a global order subject to all the ordering rules. Now that we understand at a high level how stimulus batching happens and how BatchSolve determines whether there exists a GO or not, let me just go over some of the more advanced topic which the rest of the paper deals with. One of them is atomic handling. The question is now, how do we take this framework and extend from reads and writes to atomics? And there could be different kinds of atomic: min, max, increment, decrement, compare, and swap. And there could be flavors of atomic which return data like a read and and some that don't. So the question is, how do we handle those atomics in this framework? The other thing that is particularly tricky is barrier handling in this framework. And although I won't go into all the gory details, I'd like to touch at a high level how barrier is handled in this framework. So barriers are typically used in producer-consumer thread synchronizations, where it implicitly introduces an ordering constraint between reads and writes coming from different sources. So what the bats try to do is, based on the execution, it will try to find out these ordering constraints imposed by the barriers and then present that as constraints to the solver. So again, at a high level idea is, for every barrier, we will create a set S before and S after. And a memop can go into either S before or S after, or neither, based on certain sample rules. So for instance, here's a sample rule which says reads issued after the membar act. So if you issue a barrier and the act comes back, and any read that is issued after that barrier act from either same or the different source as the barrier will need to be ordered after the barrier. So it will go in S after. So using similar rules, there will be memops which will go S before. The idea is every element in S before needs to be ordered before every element in S after. So we can remove the barrier and draw direct edges. And so this computation on edge detection is done in the pre-randomized phase, and the edges are actually presented as constraints to the XZ solver. And that's how we handle barriers in BATS at a high level. For those who are interested more, we provide links to EDA Playground, and we have created 2 demos. And the first one is a simple read-write atomic. We create one example of an execution for which geo exists, and the other one where the solver fails because there does not exist legal global order. And then we have another link for demonstrating the barrier handling case. We ran and we developed and ran BATS towards the end of the project, and we found that the initial development effort is 8 weeks compared to the POSS, which takes 80 weeks of development effort, which is a 10x reduction. Maintenance, we expect it to be nothing more than 0 to a week, because the method is immune to microarchitectural changes, and it's also very portable. If the test bench has some kind of scoreboarding, then these kind of BATS can be easily ported over in a week. However, when we ran BATS, the test runtime and the sim time both increases by 10 to 15%. This is caused by the solver runtime and also the batching scheme. In conclusion, I'd like to say that BatchSolve provides an interesting technique which is extremely low cost in terms of development and maintenance. It's highly portable, and it allows us to specify ordering rules as high-level system Verilog constraints, which can be very useful if you have memory operations going over a variety of links which have different ordering rules like PCIe, NVLink, and so on. However, BATS, due to the batching scheme, there's some slight loss of coverage and a slight increase in runtime. In future, I'm interested in seeing if we can reformulate this problem as a convex relaxation problem and use convex solvers to increase the batch size beyond what SV solvers can support. Thanks for listening to my presentation. Thank you.
Thank you, Debarshi. That was very interesting presentation, and there were actually few questions, and I know one of the question you kind of answered, but that came directly to me. But let's read through the question if you can answer it again. I think the first question is, in the point of serialization synchronization approach, I guess, what about binding, embedding, or embedding SV interfaces in the RTL? Such an approach can be done generically, addressing development and maintenance cost, and it's perfectly portable since observation point becomes anchored in RTL. So observability will be consistent across all instances of the design block.
So just making sure, Vibha, you can hear me, right?
Yes, we can hear you very well. Yeah.
So thanks, Shay, for the question. I think the problem with portability cannot, in this case, cannot be solved with a methodology, because this is not a methodology issue. Let me try to explain why. So when, let's say, two writes are coming from different sources and they are growing through different RTL blocks to a point of serialization, which is maybe located in the L2. What's happening here is we are tracking these transactions through the RTL to the serialization logic, right? Now, how to track that logic might change as the RTL change into a next project, right? So because that logic changes, and then the serialization logic might change, the cache hierarchies might change, the whole internal protocol might change. So there has to be somebody who will go and update this code now to reflect those changes. There could be, read coalescing happening, which might get introduced in a project. I mean, there are tons of things that change. And so by just, it cannot be made portable by a methodology change in this case. I hope that answers the question, but that's the thing.
Okay, just to follow up on that, let's say even if you restrict just in few places, let's say at L2 level, and then at the L1 level, where the hierarchy is kind of already known, right? So if this kind of, binding the interface close to the RTL, it's like, that's the source of it. And then if you restrict instead of putting everywhere, and I understand, the hierarchy and everything can change, but if you restrict just the L1, L2, and the L3 in that way, would it still add benefit?
Yeah, I mean, all those methodology things should be done, but that is a totally different approach. In POS's approach, we do that. And we have seen historically there's a lot of kind of effort needed to maintain that. In the batch approach, we only tap the duty interface signal. So in this approach, we only need to look at what memory operations and attributes were driven on the DUT boundary, the acknowledgements coming back. And based on that, what we're trying to do is we're trying to answer the question that can we order the memos or determine a global order, which are subject to all the ordering rules. So yeah, so we don't even tap any internal signals in this batch approach.
Okay, thank you. Thank you for clarifying that. The next question is about what is the definition of a sector? I know you answered that question. And
yeah, so I'll just reiterate that the sector here is, I don't want to go into the architectural details, but in this paper, sector is the ordering granularity. So it's possible that a memory operation can cross over the ordering granularity. Let's say there are two writes, and in this case, let's say sector is the memory ordering granularity. So it's possible that two writes spawn two sectors, both of them. And when you look at write sector 0, it's possible that writes are, hold on for a second. Yeah, so when you look at sector 0, that writes 1 is ordered before write 2. And when you look at sector, the other sector, the writes are ordered in a different way. So when memory operations cross over sectors, we break them into child and then look at a sector and try to find out if the global order exists in that sector.
Thank you very much. I think this is the last question. We're already out of time. How do you handle faults or kills?
Faults or kills happen inside the RTL, right? So we don't want to order faults or kills in the ordering of memory operations. So they don't go into global order. Like internal events, there could be invalidates happening. There could be tons of things happening in the RTL. Those don't go into determining whether a global order exists or not. Hope that helps.
Okay. Okay, and there is one more question. I'm going to skip on that because we're already out of time, and it is there in the chat. If you can answer that that person, I think it is
Sure.
from Nehajin. That would be really great. And I want to thank you for coming here today and giving us the recorded presentation. And it's been wonderful to listen to. Thank you very much. Thank you. And to all the attendees, please don't forget the past 2 papers in the voting section. With that, let's move on to the last paper. The last paper is on CAMEL. It's interesting analogy. CAMEL stands for cache model, a flexible cache model for cache verification. And a presenter today going to be, I'm going to try pronouncing her name, Yue Liu, I guess. And so she is coming from Mediatek today. She has completed her bachelor's and master's from Jiatong Beijing University on electronic science and technology. Since 2018, she has been working for Mediatek Corporation. And let's welcome her. But of course, we are going to actually present the recorded presentation. Let's start the presentation.
Hello, ladies and gentlemen. My name is Liu Yue from Mediatek Corporation. Today, our topic is CAMEL, a flexible cache model for cache verification. My colleagues Liu Fang, Song Yunyang, and I work for this topic together. The cache model will be introduced in the following 4 steps. First is design overview. I will give a brief introduction of the design of the verification. Second is CAMEL model structure. I will detailed introduce our model, CAMEL model, in this part. And then I'll introduce the attributes adding to the CAMEL model to achieve the precise check. And finally, I will give a summary of the CAMEL model. First, let's focus on the design overview. Our DUT is the level 1 cache of a CPU IP design, and I'll call it L16 in short in the following introduction. To reach high performance, the core supports multi-thread. Each thread is independent. And also for high performances, L16 has many internal buffers to increase the efficiency of load and store instructions. And in L16, there are I cache, which is instruction cache, and the D cache, which is data cache inside the L16. Just I cache is the instruction cache is only a read-only cache and simple on the data flow. So we mainly focus on data cache, D cache today. This is a D cache. This is a D cache in the diagram. The detailed buffer are shown in the right diagram. All the buffers' purpose in L1D D cache is to shorten the time of the cache miss, which is reduce the miss penalty. In order to explain the complexity of L16 clearly, I will give a more detailed description in these 2 perspectives. First is multi-thread characteristic, and then I will give a basic data flow. This is a multi-thread design. Each thread is independent, which means the instruction types, the instructions each thread can send are the same, And in some ways, it can be recognized to the two cores or multi-cores. One thread's cache miss will not store other threads, and the multi-thread will influence each other by sharing the common buffers. And that means the multi-thread or two thread can access the same address region, and in this way, L1 cache can be recognized to it not only achieve the cache behavior, but also do the multi-thread coherence also. And let me take the basic data flow as an example. There are a shadow command buffer, which is SCB here, store buffer, which is STB, and the line filling buffer LFB, and the eviction buffer EB here. If load or store instruction comes to L1 sys, if there hit cache, it reaches cache hit, and the data flow is simple, they will read or write cache directly. But if they miss cache, and if they get a cache miss, for a load instruction, it will go to shadow command buffer, and for a store instruction, it will go to store buffer. Both the shadow command buffer and the store buffer will send a read request to fetch the cache line for the cache miss, and to send the read request to the external memory. And after the external memory is sent back to the read data to the L1 sys, the cache update happens, and the data will pass through line filling buffer and to the SRAM to do the cache update. And if the eviction happens during the cache update period, the victim data will be written to the external memory through the eviction buffer. These are the behaviors these buffers will do. And for L1 sys design, we do have a test bench before. Since the behavior of each buffers are complex, we create the precise behavior model for each of the buffers to verify the behaviors. Then this can precisely segmentedly verify the data flow, but if design changes in any of these buffers, the behavior model must change, and exactly the same as the design changes. And before the changes are ready, the simulation cannot run and start to verify. So this kind of test bench really put much effort on DV and the design engineers. So we prepare to change this, we decide to change this circumstance. We propose a new model, CAMEL model, to replace all the previous behavior models. And then let me introduce for the new cache model, CAMEL model. CAMEL is the abbreviation of a cache model. The basic goal of the CAMEL model focus is data correctness. This is achieved by comparing the read data. When the load instruction comes from the core, the RTL will give a read data, and our test bench will also predict a read data. We compare the read data if they are the same to judge the logic of the cache is correct or not correct. As for CAMEL model structure, CAMEL's basic storage unit is this kind of info. And this info includes address and data and other attributes. The most important attributes are valid and dirty flag. And the CAMEL model offers two kinds of view of data. The one is byte view. This info unit is 1 byte. 1 byte address corresponding to its data, to its byte data, and valid and dirty. For core accessing the L1 normally the instruction will access 1 byte or 2 bytes or several bytes. The unit is a byte, so the byte will directly modify the CAMEL's corresponding info. And this is useful when core accessing the L1 sys. And then there's another view, cache line view. When there is also other operations like cache operations or cache updates that I just introduced, these data flow units are cache line, and these will operate the whole cache line. So the cache line view is also needed. And this view is achieved by the APIs in CAMEL model. And to summarize CAMEL model, it's just like what the camel word, the animal word, it means. The data in CAMEL model is just like the water in the camel. No matter what view you are using, the byte view or the cache line view, the data in the CAMEL model is just like the water in the camel animal, they are the same. And after the introduction of CAMEL model structure, next I will introduce how CAMEL model works in the verification environment. This diagram is how CAMEL model placed in our DV environment, and this is an example. Let us focus on thread 0 firstly. When a load instruction, the address is 104, comes to L1 sys, it meets the cache, and the CAMEL model will record a info that is address is 104, data is unknown, valid dirty are 0 into the CAMEL model. And in design, it will goes to shadow command buffer and send read request to external memory. And after the data is come back from external memory, the data will be updated and the value will be 1. And then this time, L1 sys will inform the core that the data is back. You can fetch the data. Again, we call this redo. And when the core resend this load instruction, it will get the data. It's what the cache needs behave in the L1 sys. And from this point to this point, the thread link is solved by this load miss. But as what we just introduced, thread 1 is not it will not be stalled by thread 0's cache miss. It can send instructions, and the address region is low limited. So thread 1 may send the store instruction to the same address 104 at time A or time B. Let me set let us set the data is 34 to the cache, and adding this behavior at time C, thread 0 get the data maybe 12 or 34. Both of the data values are reasonable from server view, since the L1 sys are now responsible for the data spread value when both threads are accessing the same address. So they're both acceptable, but the RTL will give a certain data based on the timing, but we do not know the timing. So CAMEL model will record both of the data values into the data queue, and when the RTL read data appears, we compare them both to the RTL read data. If the read data is in this range, the CAMEL model will judge it is correct. And in this case, in this way, we use this simple CAMEL model and to verify the L1 complex design in a acceptable precision. In previous example, the accuracy of the check precision is acceptable, but not precise enough. In the early stage of the verification, it can quickly build up the test bench based on the simple CAMEL model. But for later stage in verification, we provide more attributes to achieve more precise check. So what other checkers do we need? First is precise data check. The simple CAMEL model can only offer a data range, but this range needs to be smaller or even a certain data value. Next is the reasonability check of the request to external memory. The read request L1 sent to external memory will influence the bandwidth of the whole core to the external memory. The bandwidth is important, so there can be that's useless read request to send to the external memory, and this is also need to be checked. The third is hit miss check. Since our basic goal is data correctness, and we compare we compare the read data for the cache correctness, and when any of the instruction comes to L1 it will judge hit or miss. If this judge has bug, the load instruction it will influence its performance, and for store instruction, if we can judge if we can find bug here, we can debug the debug access will be much easier. So we add these attributes, location, and some other data space to achieve these checkers. And the next, I will introduce how this achieved. First is location. As the word represents, it means where the data is locating. And then is shadow command buffer data. This offers extra space for data check. And there can be added other attributes in CAMEL model if needed. And let me introduce how this works. Take location as an example. When the cache hit, it will read or write directly, and I will not introduce. And when cache miss, if the load miss, the starting location is nowhere. If a load miss comes to L1 we will create a info and change the location to shadow command buffer. And if it is a store miss, the location will change to store buffer. And then if we see the read request at the interface between L1 and external memory, we will change the location to external memory. And after the data sent back from external memory, the location will change to line filling buffer and SRAM along the cache update process. So at this point, if a instruction comes to L1 we can search for the infos, CAMEL model records, and with the help of the location, we can judge it is hit or miss here, and compare to the RTL's judgment. And at this point, if we see a request happens here, we can judge from this address and see whether it is reasonable. And this is to reduce not meaningful request. And let us focus on the example I previously mentioned. With the help of shadow command buffer data and location, the previous example will be more precise. If the first step is the same, when the instruction comes to L1 and send request to external memory, the location will become to external memory, and if the store data comes at time A, the store data will be recorded at SRAM data, and the dirty flag will change to 1. And at this time, the read data are not comes back. So when the data comes back at catch update process, the written data will be merged to will be considered and merged to what thread 0 will see, and the thread 0's data will be 34. And so when the core gets back the load data, the data will be 34. And if the instruction thread 1 sense comes at time B, at this circumstance, the read data from external memory update here, and the data will be preserved as 12 to the thread 1's buffer, and this will not change even the store instruction from thread 1 comes at time B. It will be preserved at 12 until the thread 0 gets data back. So from this view, the true data values range will become to one certain data. And these, in this way, the 3 checkers we just mentioned are achieved. And let me give a summary of the CAMEL model. The basic CAMEL model is designed in a simple structure and can offer a acceptable precision for the basic data check. The CAMEL model with extra attributes can offer more and support more checkers, more precise checkers, and also it is more complex. And the adding attribute location is not only helpful for the precise check, but also can feed back to stimulus. And in this way, we can have more complex stimulus and find back more quickly. And this is the CAMEL model's coding lines comparing to behavior of the previous buffer behavior model. The CAMEL model is more general and more able to reuse in many cache verification environments. This is a coding line comparison. And that is all for my introduction of CAMEL model. Thank you.
Hello, ULU. Thank you for recording the presentation, and we are already well ahead of over time, and I'm going to skip the QA session here because there was one question, and ULU already answered that question, and there are no more questions, and I encourage the attendees, just read through the chat for that answer. But I want to thank all the attendees and all the presenters today. This was a very wonderful technical presentation. I really enjoyed, and I hope all attendees you also enjoyed. Please don't forget, actually, vote for these papers today, and please enjoy the rest of the DVCon sessions. Thank you very much.